Have you ever wondered what really brings incredibly complex software to a grinding halt? We're about to dive into the invisible traffic jams happening deep inside our computers, these tiny glitches that can have very real and sometimes very tragic consequences.
So this number, it's not just random. 347 is the number of people who tragically lost their lives in two separate crashes of the Boeing 737 MAX. It's just a stark, sobering reminder of how high the stakes really are.
And here's the critical part. The cause wasn't a faulty engine or some other mechanical problem. The root cause was a software error, a specific kind known as a concurrency bug. This is what happens when a program tries to do way too many things at once and, well, it basically gets tangled up in itself.
And this Boeing incident, it wasn't some one-off thing. These kinds of digital standoffs can happen in all sorts of systems we rely on every day, and the stakes are often unbelievably high.
Think about this. A decade before those tragedies, Toyota had major issues with cars suddenly accelerating on their own, and that was also linked to a concurrency problem in their software. So we're talking from the sky to the road. When these programs fail, the results can be just catastrophic.
So how do we even begin to wrap our heads around such a complex failure? Well, a fantastic way to do it is to look at a classic thought experiment from way back in 1965. It's called the Dining Philosopher's Problem, and it was designed by the famous computer scientist Edgar Dijkstra to model this exact issue.
Okay, so picture this. You've got 5 philosophers sitting around a circular table. Their life is simple. They either think or they eat. But here's the catch. There are only 5 chopsticks on the table, with one place between each philosopher. To eat, a philosopher needs 2 chopsticks, but they can only grab the one on their immediate left and the one on their immediate right. Now, the process for each philosopher seems perfectly logical, right? First, they think. When they get hungry, they pick up the chopstick to their left. Then they reach for the one on their right. Once they have both, they can finally eat. I mean, it seems like a totally foolproof plan. But, and this is what's so fascinating, this simple logical system can completely and utterly break down. And this elegant little problem perfectly illustrates the 3 major ways that concurrent systems, like the ones in planes and cars, can fail. So this little thought experiment, it reveals 3 critical failures. These are like the ghosts in the machine that programmers are always trying to avoid. Deadlock, livelock, and starvation.
The first one, and probably the most famous, is the deadlock. And it's exactly what it sounds like. It's a complete and total standstill, where every single part of the system is just frozen, waiting for something else to make a move that, well, is never going to come.
So here's exactly how it happens at the table. Imagine every single philosopher gets hungry at the exact same moment. They all reach out and grab their left chopstick. Now what? Every person is holding one chopstick, waiting for the one on their right, which is of course being held by their neighbor. Nobody can eat, nobody can put their chopstick down, the entire system is frozen solid forever.
The second failure is a little bit sneakier. It's called a livelock. And in this case, the system actually looks busy. Things are happening, states are changing, but no actual progress is being made. Everybody is just spinning their wheels. You know, a great way to think about the difference is this. A deadlock is like 2 people meeting in a narrow hallway and just stopping, each waiting for the other person to move. A livelock is when they both try to be polite and step aside in the same direction, then step back the other way, over and over again in this awkward dance. They're active, but they're still stuck. They're trying forever instead of waiting forever. And the final failure. This one isn't really about the system stopping at all. It's about the system being fundamentally unfair. This is called starvation. It's where one process is just constantly denied the resources it needs to do its job, usually because other, greedier, or maybe just faster processes keep getting to them first. In our little model, this could happen if one fast-thinking philosopher is just quicker on the draw and keeps grabbing both chopsticks before anyone else has a chance. I mean, look at this chart. Philosopher number 1 has eaten over 400 dumplings, but poor philosopher number 9, who was maybe just a little too slow each time, got 0, none. They were just perpetually unlucky and effectively starved. Okay, so if these problems are so common and so dangerous, how in the world do software engineers design systems to actually prevent them from happening in the first place? One of the most elegant solutions is to just introduce a central controller, sort of a referee. We can call it an arbitrator. In our dining analogy, this is like having a waiter at the table who's in charge of all the chopsticks. And the rule is simple. A philosopher has to ask the waiter for permission before they can even touch a chopstick. The waiter acts like a gatekeeper,
making sure only one philosopher at a time can even attempt to pick them up. This completely prevents that scenario where everyone grabs just one, which, as we saw, is what causes the deadlock.
Now that's one way. But here's another really clever solution. You can break the symmetry of the problem by imposing a strict order on everything. This is called a resource hierarchy. You simply number all the resources, in our case the chopsticks, and then you create one simple unbreakable rule.
And the rule is this: you must always try to pick up the lower numbered or higher priority chopstick first. By forcing every single philosopher to compete for the chopsticks in the exact same order, you completely prevent that circular "I'm waiting for you, you're waiting for me" problem. The standoff is broken before it can even begin.
So, philosophers, chopsticks, how does this abstract little problem connect back to the actual technology that's powering our entire world?
Well, the lessons from this simple table are absolutely critical. I mean, these aren't just logic puzzles for academics, they represent fundamental challenges in engineering reliable tech. And while the best defense is to just design things so you don't have to share resources, when you can't avoid it, these synchronization strategies are essential, even if they slow things down a little. At the end of the day, understanding and preventing things like deadlock, livelock, and starvation is absolutely essential for building safe and reliable technology. And this applies to everything, from the flight control software in an airplane to a medical device, all the way down to the operating system on your phone.
And that really leaves us with a final, pretty big thought. As our world becomes more and more dependent on incredibly complex, concurrent software, the responsibility to build it right just grows and grows. It's not enough for our code to be fast and powerful anymore. It absolutely has to be robust, safe, and fair for everyone.